This first stage exists for one clear purpose: to ensure that every material entering the UAV production line is predictable, traceable, and suitable for aerospace-grade manufacturing. From my experience inside industrial plants, this step is often underestimated, yet it determines how stable and repeatable the entire process will be later on. If the material is inconsistent at this point, no amount of precision machining downstream can fully correct it. The process begins with the sourcing of aluminum aerospace alloys, carbon fiber sheets, composite resins, copper conductors, and semiconductor-grade electronic components. These materials arrive from specialized suppliers and are unloaded using automated dock systems equipped with weight sensors and RFID scanners. Each batch is immediately registered into a digital inventory platform, where its origin, composition data, and delivery conditions are logged. In practice, this digital traceability is what allows engineers to trace a performance issue back to a specific material lot months later. Next, the incoming materials pass through an inspection zone. Optical scanners verify surface integrity, while spectrometers analyze chemical composition without damaging the material. Carbon fiber rolls are checked for fiber alignment and resin distribution, and electronic components are tested for static discharge tolerance. I have seen how skipping even one of these checks can introduce invisible weaknesses that only appear during flight testing. That is why this stage operates slowly and deliberately compared to later phases. The operational flow is linear and controlled. Materials move from unloading to inspection, then to classification, and finally into climate-controlled storage. Aluminum and composite materials are stored in humidity-regulated chambers, while electronic components are sealed in anti-static containers. The input of this stage is raw industrial material with variable conditions. The output is certified, labeled, and stabilized material, ready for controlled processing. Before we move on, it is important to understand that nothing here is about speed. This step is about discipline and consistency. Once materials leave this area, they are no longer questioned, they are trusted. And that trust is what allows the next phase, material processing and standardization, to operate with precision instead of correction. 2. The purpose of this stage is to transform certified raw materials into stable, uniform inputs that behave predictably during precision manufacturing. From a factory perspective, this is where uncertainty is systematically removed. Materials that were verified in the previous stage are now physically altered so their mechanical, thermal, and electrical properties match engineering specifications exactly. In my experience, this step is what allows a production line to run without constant recalibration. The process begins with metals and alloys entering controlled thermal treatment systems. Computer-controlled heat treatment furnaces adjust hardness, tensile strength, and internal stress profiles according to predefined material recipes. Aluminum components are heated, held, and cooled in precisely timed cycles, while atmosphere control systems prevent oxidation. At the same time, composite materials, such as carbon fiber panels, are placed into vacuum-assisted molding stations and autoclaves, where pressure and temperature are applied to create consistent internal bonding. Once primary treatment is complete, materials move into shaping and preparation. Automated cutting tables and CNC pre-forming machines trim metals and composites into standardized blanks. These machines operate from digital models, ensuring dimensional repeatability across large production batches. Electronic materials follow a different path, entering cleaning and coating stations where ionic contaminants are removed and protective layers are applied to reduce electromagnetic interference. I have always considered this part less visible but equally critical, because electronic reliability depends heavily on surface preparation. Quality verification follows immediately after processing. Ultrasonic inspection systems scan composite structures for voids or delamination, while industrial X-ray machines examine internal metal integrity. Electrical materials are tested for conductivity and insulation stability. The operational sequence is deliberate: process, verify, and only then release the material forward. The input of this stage is certified raw material. The output is standardized, dimensionally stable material prepared for precision machining and assembly. As someone who has watched production lines succeed or fail, I can say this phase is where materials stop being raw and start behaving like engineered components. With their properties stabilized and documented, the manufacturing flow can now move forward with confidence. That leads directly into the next stage, where these standardized materials are shaped into individual UAV components through high-precision mechanical and digital fabrication. 3. The objective of this stage is to convert standardized materials into fully defined UAV components that meet exact geometric and functional requirements. This is the point where design data becomes physical hardware. From a production standpoint, this phase is about accuracy and repeatability rather than volume. If tolerances drift here, the effects will surface later during assembly and system integration. The process begins with digital manufacturing data being loaded into the factory control system. 5-axis CNC machining centers shape aluminum and alloy blanks into structural frames, motor mounts, and load-bearing brackets. Laser cutting systems process composite panels into aerodynamic skins, while industrial additive manufacturing machines produce complex internal parts that cannot be milled conventionally. All machines operate under centralized monitoring, allowing real-time adjustment of cutting speed, tool wear, and thermal expansion. Once primary machining is complete, components move to secondary finishing operations. Deburring machines remove sharp edges, surface treatment stations apply corrosion-resistant coatings, and precision grinding ensures critical mating surfaces meet micron-level tolerances. In parallel, electronic components are assembled on automated surface mount technology lines, where robotic placement systems position micro-components with consistent accuracy. From my experience, this separation between mechanical and electronic production reduces cross-contamination and improves long-term reliability. Inspection follows immediately after fabrication. Coordinate measuring machines verify dimensional accuracy, while optical scanners compare finished parts against digital models. Electronic assemblies undergo functional and continuity testing before being approved. The input to this stage is standardized processed material. The output is a set of verified mechanical and electronic parts and electronic modules ready for system-level assembly. I often describe this phase as the moment the UAV begins to take shape, even though nothing is assembled yet. Every component produced here must fit without adjustment later on. That is why this stage focuses on control rather than speed. With all parts now defined and validated, the production flow naturally advances to the next phase, where these individual elements are brought together through structured assembly and system integration. 4. The purpose of this stage is to combine individual components into a complete UAV platform and verify that all systems operate together as designed. Up to this point, every part has been produced and tested in isolation. Here, the focus shifts from individual accuracy to system-level compatibility. In my view, this is where manufacturing discipline becomes visible, because small inconsistencies that were acceptable earlier will now immediately reveal themselves. The assembly process begins in a controlled production cell where mechanical structures are fixed into calibrated assembly jigs. Robotic arms and torque-controlled tools install motors, transmission elements, and structural fasteners in a defined sequence. Once the airframe is mechanically complete, electronic modules are installed, including flight control units, power distribution boards, navigation sensors, and communication systems. All connections are guided by digital work instructions displayed directly at each workstation, reducing human variation. After physical assembly, the UAV enters the integration phase. Software is uploaded to the flight control system, and sensors are calibrated using automated alignment stations. Power systems are activated under load using diagnostic benches that simulate operational conditions without allowing free movement. From experience, this is the stage where engineering assumptions are either confirmed or corrected. A system that works perfectly on paper must now function as a coordinated whole. Functional verification follows immediately. Each subsystem is tested in sequence: propulsion response, signal transmission, sensor feedback, and control logic. Data from these tests is recorded and compared against baseline performance models. The input to this stage is a complete set of verified components. The output is a fully assembled UAV with confirmed functional integrity, ready for final finishing and environmental testing. I often explain this phase as the transition from parts to a machine. Nothing here is experimental, and nothing is improvised. Once assembly and integration are complete, the UAV is no longer just manufactured, it is operational. That naturally leads into the next stage, where the focus shifts to surface finishing, durability validation, and preparation for long-term storage and deployment. The purpose of this stage is to confirm that the assembled UAV is durable, compliant, and ready for controlled storage or deployment. From a manufacturing perspective, this is not about adding features, but about verifying that nothing has been compromised during earlier stages. I often describe this phase as the point where the factory takes responsibility for the entire system, not just its parts. The process begins with surface finishing. The UAV is transferred into automated coating booths where protective layers are applied using robotic spray systems. These coatings are selected to reduce corrosion, manage thermal exposure, and protect sensitive surfaces without affecting aerodynamic performance. Once cured in controlled ovens, the airframe moves into a marking station where identification codes and traceability labels are applied using laser engraving technology. Next comes inspection and validation. The UAV enters environmental test chambers that simulate temperature variation, vibration, and operational stress. Diagnostic software runs extended system checks while the aircraft remains stationary, monitoring power stability, sensor behavior, and communication integrity. In my experience, this step often confirms decisions made much earlier in material selection and assembly discipline. A stable result here usually means the process upstream was well controlled. After testing, protective measures are applied. Sensitive components are sealed, connectors are capped, and transport locks are installed on moving parts. The UAV is then placed into a custom protective container with shock absorption and humidity control. The input to this stage is a fully assembled and functional UAV. The output is a validated, protected system cleared for storage and logistics handling. I see this phase as the quiet confirmation stage. There is no adjustment, no correction, and no redesign here. Everything either holds or it does not. Once this step is complete, the UAV is considered production ready. From here, the process moves naturally into the final stage, where storage conditions, inventory control, and secure transportation ensure the system remains exactly as it left the factory floor. The purpose of this final stage is to preserve the UAV exactly as it left the production line and ensure it can be deployed or delivered without degradation. From an industrial standpoint, manufacturing does not truly end when assembly is finished. It ends when the product remains stable over time. I have always considered this step less visible but essential, because even a perfectly built system can lose reliability if storage conditions are poorly managed. The process begins with transfer from the finishing area to the logistics zone using guided transport carts. These vehicles follow predefined routes and minimize vibration during movement. Each UAV, already sealed in a protective container, is scanned into the warehouse management system, where its configuration, inspection history, and storage requirements are automatically linked. Climate-controlled storage rooms maintain stable temperature and humidity levels, while air filtration systems reduce particulate contamination. Storage operations follow a strict sequence. Containers are placed in designated zones based on battery status, deployment priority, and inspection cycle. Sensors continuously monitor environmental conditions, and any deviation triggers alerts to maintenance teams. From experience, this level of monitoring is what turns storage from a passive activity into an active part of quality assurance. Nothing here is left to assumption. When transportation is required, the process reverses in a controlled manner. The UAV is retrieved, re-verified digitally, and loaded onto specialized transport platforms designed to absorb shock and limit movement. The input to this stage is a fully validated, protected UAV. The output is a system that remains production-ready, whether it stays in storage or moves toward deployment. I often explain this phase as the moment the factory lets go. No further changes are made, and no improvements are added. The responsibility shifts from manufacturing to logistics discipline. With this step complete, the UAV production cycle is closed, and the system is preserved exactly as intended, ready for its next operational environment.